Okay, we are here with our students to talk about building sequences. And this is where your function notation is going to start coming in a lot handier for you. Okay?
Okay.
So what we're really trying to do is we're trying to make the way that we write about functions simpler and more useful for us. Okay?
Okay.
So, and we're going to focus only on arithmetic sequences here. Okay? So let's take a look at an infinite arithmetic sequence. We have the first 4 terms of the sequence here. And then let's just say what we think the first term is and the common difference. So what's the first term?
2.
2, good. And what's the common difference? It's the amount that you change when you go from term to term.
3.
Positive 3, right? Okay. So first term is 2, common difference is 3. And we can write that out in function notation, and this is going to be a lot of kind of heavy function notation, but don't worry, it'll get simpler in a second. We can say the first term, f of 1, is 2. That's what that says, is the first term is 2. If I said f of 2, that would be the second term. Okay? So first term is 2. That's basically what you're saying right here. And then we're saying to get to the next term, take your current term and add 3. In other words, the common difference is 3. So this whole statement right here is a way to describe this infinite arithmetic sequence. And it's a little clunky, okay? So, and it has a lot of function notation in there, but you can get used to this. And we call that a recursive definition. It's basically saying you have to know one term to get the next term. It kind of recurs that way, okay?
Okay.
Now, there's a different kind of a definition that now we're going to try to develop, okay?
Okay.
And it'll be more useful for you, and it won't have its function notation won't be as heavy. So I think you'll probably like it better. Okay, so we're going to try to come up with it. It's a simpler statement, and it's also good for predicting. Okay, so let's just really quickly say what we want to predict something is we want to say f of n. So you tell me whatever term you want, the 5th term, the 90th term, the 10 millionth term. That's what I want to do. I want to be able to predict. So we want to get something that just basically says f of n equals. Okay, and then so let's take a look at this. We're going to put in another column up here on our table to kind of guide us and see how we can create this function down here, okay? So with the first term, we were at 2, and we hadn't added 3 any times yet. So the number of times we had added 3 was 0. Okay, does that make sense so far?
Yeah.
Okay, with the second term, we're at 5. We'd added 3 one time. Okay, makes sense. With 8, we'd added 3 how many times?
2 times.
Okay, and with 11, we'd added 3 how many times? 3 times, yeah.
3 times,
okay,
yeah.
good. So now let's compare what n is, the term, with the number of times we added 3. Okay, can you see any pattern here between these numbers right here? What's the number of times we added 3 compared to n?
It's a -1.
Yeah. It's n minus 1, okay? So to get any term in the sequence, what we're going to do is we're going to take 3, we're going to add it in n minus 1 times, okay?
Okay.
So if it were, and then we still have to not forget that initial value, so then we'll add 2, okay?
Yeah.
So let's just make sure that this makes sense. If we have the third term, we put 3 in for here for n. That's the third term. So we would have f of 3 equals 3 minus 1 is 2. 3 times 2 is 6. 6 plus 2 is 8. That's our third term, right?
Right.
Okay, so we have a function now that's f of n, and it's a lot simpler than writing this whole thing up here. And let's test it out. Let's predict what the 10th term would be, okay? So we'll say, okay, f of 10 equals, and then we just put 10 in for n here. So 3 times, instead of n minus 1, it's 10 minus 1, plus 2. Okay, let's go ahead and simplify. What's 10 minus 1?
9.
Okay, so we have 3 times 9 plus 2. What's 3 times 9?
27.
Plus 2 is?
29.
29. So the 10th term is going to be 29. See how simple that is?
Oh, yeah.
Okay, so that's a lot better. But you know what? I don't think this is quite simple enough. Because we can simplify this right here, right? We can use our distributive property. So let's try to make this even a little bit more simple. We'll take 3 times n times 3 times -1, so that's 3n minus 3. And then how can you simplify this a little bit further?
Oh, you can combine the -3 and the 2.
Yeah, so then we'll just have f of n equals 3n minus 1. Now, isn't that the simplest thing ever? It's so much simpler than this recursive function here, and it allows us to predict. So we call this an explicit function, and it's really useful for predicting. For instance, if I said, what's the 100th term? What would you do? What would you plug in here?
Well, you would have 100.
So you'd have f of 100 equals, and then what would you do?
You would say 3 times 100.
And so let's go ahead and start writing this out. F of 100 equals 3 times 100 minus 1, which is
299.
299. And just like that, you found the 100th term. If you'd had to do it with your recursive function, you would have had to say, okay, let's add 3 another time. Okay, let's add 3 another time. You would have done that 100 times. It would have taken you forever. Here, because we found an explicit function, we can predict really quickly.
Yeah.
Okay? So and that's why this function notation is super helpful too, because you can just say f of 100 equals 299. It's the simplest way to say the 100th term of this infinite arithmetic sequence is 299. Okay?
Okay.
All right. Now, let's build on this knowledge, and let's say, okay, if we have this recursive definition right here, something that looks like this, how can we quickly convert to an explicit function here? Okay? You'll get used to this once we do. The first time through it, though, we have to kind of wrestle with some stuff. Ooh, here's another one of those recursive definitions. Tell me what this part means here.
The first term is 27.
Perfect. And tell me what this part means here.
Let's see. So to get to the next term, you would get the current term minus 2.
Right. So what's the common difference then?
Minus 2.
Good. And that's excellent that you said minus 2 or negative 2, because you want to really pay attention to that symbol here. So we can say the first term, as you said, is 27, and the common difference is negative 2. Okay?
Okay.
So let's go ahead and create a table here. We have your n here, like we always set up. What's the value that should go here then?
27.
Good, because that's our first term. Okay, now what's the value that should go here?
25.
25. And how did you know that?
I took 27 and I subtracted 2.
Because that's our common difference, right?
Right.
Okay, good. So that's 25. Help me fill out the rest here.
Okay, the third term is 23.
Okay.
And the fourth term is 21.
Perfect. Okay, good. Now, so that's how we would create a table from our recursive definition here. But now let's try to create an explicit function. Okay, so we want something that looks kind of like what we had over here. So we're going to say f of n equals, and if you remember, what we did here is we took that common difference and we multiply it by n minus 1. And it's always n minus 1 because you're not going to do it the first time, but you're going to do it every other time. So it's going to be n minus 1. So what's our common difference here again?
Minus 2.
Okay, so we're going to take negative 2 and we're going to multiply that times n minus 1. But then we can't forget this last little piece here. We have to add what?
27, the
Right.
first term.
Our initial value, our first term. Okay, so now that's pretty good, but we can simplify it further. So let's go ahead and do that. F of n equals, can you apply the distributive property for me there and tell me what to write?
Yeah, negative 2n plus 2
Good,
plus 27.
good. And then let's simplify that a little bit further. What should we write? Negative 2n plus 29, right? Because we add the 2 and the 27.
Right.
And there is our explicit function that we got from this recursive definition. So this looks a little confusing, kind of hard to write, but we can take it down to here. And again, this will be really great for predicting. Okay, last thing, what if we're given this and we want to, for some reason, get up to here? Okay, that's the next thing we're going to try here. Oh, sorry. Let's first acknowledge here. This is great for predicting. So if we wanted the 12th term of this sequence here, you just say f of 12 equals, and then we just put in 12 for n, negative 2 times 12 plus 29. Negative 2 times 12 is negative 24. Negative 24 plus 29 is what?
5.
5. So then we would just say f of 12 equals 5. That's the simplest way for us to say the 12th term is 5. Okay, and that's why function notation can really start to save you time. Okay, now it's time for us to take an explicit function and try to move up to a recursive definition, okay?
Okay.
And we'll do that over here on the right-hand side. So let's say that we're given an explicit function that looks like this. F of n equals 8n minus 14. Okay? Now, probably the simplest way is just to ask ourselves that same questions. What's the first term and what's the common difference? Okay, so let's create some space for that. Now, the first term, how would you figure out what the first term is? And I'll give you a clue. Think about what we just did down here with the 12th term.
Okay. So the first term, I would guess, is minus 14.
Okay, that's a good guess. But let's go ahead and use our n's here. Okay?
Oh.
So we're going to go ahead and put f of 1, because that's the first term, equals 8 times 1, right? That's n, minus 14. Okay, then we would say, okay, that's 8, because 8 times 1 is 8, minus 14, and that's negative 6. So that's you did something that most people do, is you think that you're going to, for some reason, it's going to be this number over here that is the first term, but don't get fooled by that. What you actually have to do is put your 1 in for your n. Okay?
Okay.
So our first term is negative 6. Now, this one's tricky too. What's the common difference here? Now, and to figure this out, think about what we did with the common difference when we were writing these explicit functions and what this coefficient of the n was here. So over here, the coefficient of n was what?
Minus 2.
Negative 2. And what was our common difference?
Minus 2.
Okay. Here, the coefficient of n ended up being 3. What was our common difference here?
3.
3. So here, what's the coefficient of n?
8.
So what is our common difference?
8.
8. And that's the trick, okay? So now you have the first term and the common difference. You can write your your recursive function. So we just write f of 1 equals negative 6, which just basically means the first term is negative 6. And then you say, to get the next term, take your current term and add the common difference, which is 8.
Okay.
Okay, so that's how you move the other direction from an explicit function to a recursive definition. And we could create a table that says, okay, our first term is negative 6, and then each time we add 8, and that's how you could build a table too off of the recursive. Make sense?
I see, yeah.
Okay, good. So a little bit about sequences, a lot about explicit and recursive ways of writing the functions about this. But really what we're driving towards is really easy ways to use functions to do predicting. And now that you know these different things, you can do that. Great job.
I see. Thanks.